Hi, my name is Cody Doucette. I'm here with Yao Chao, Guanshan Zhang, Shigang Zhu, and we are the Maple and ODL team for our cloud computing class in spring 2015. The mentor for our project is Andreas Volmy. The broad goal of our project is it's very SDN and OpenFlow based. Just to give you a broad overview of what SDN is it stands for Software Defined Networking. And it's a mechanism that separates the control and data planes. So instead of in the traditional approach where you have the control plane distributed between many nodes in the network, you can pull the control plane out of the network into a centralized controller, which then makes decisions, control decisions for the rest of the nodes in the network. And the way that it communicates between the switches and the controller is via some standard protocol, which is usually the OpenFlow protocol, but it's not necessarily the case. So this programming model has enabled a lot. It's enabled flow tables to be the standard data plane abstraction in networks. And it's also brought about a protocol for this switch and controller interaction. And all of that is great, but we're still missing a key piece to realize the full benefits of this abstraction, which is a programming language and some greater programming abstractions to make this better for users. The current practice for SDN programmers is to be very explicit about how they're going to specify flow patterns. So they usually have to do it in a declarative way, meaning they have to specify what they want the flow patterns to be, but not necessarily how they want them to be in place. They usually have to worry about low-level details, such as managing the different patterns in the flow rules. They have to worry about priorities and things like timeouts. And the programming languages that they use can be kind of restrictive. They often have to use specialized programming languages to do this. On top of that, there's other problems, such as needing to maintain consistency as the network changes, for example, as ports come up and down, or as links come up and down, and as policies change. There's different OpenFlow standards. They have to worry about switch hardware diversity. And they also have to worry about scalability and distribution concerns, or how the flow rules get distributed throughout the network. All of this can make for a very frustrating experience for the programmer. So instead, we can take another approach using an algorithmic model. And what the algorithmic model is basically just where the programmer defines a function f, which is a high-level function. And it's high-level because all it needs to know is the packet and some kind of environment. And it's going to take in those parameters and output a route. So this is going to describe how the packet should be forwarded, but it does not describe how the flow tables are configured. So now we're describing more of the how and not so much describing the what. The goal is to make this high-level function f be defined using a general-purpose programming language. So you could envision using Java or Python, or maybe even a functional language like Haskell. And then the controller is going to conceptually run f on every packet entering the network. So here's an example of a simple policy f that just contains a map to map MAC addresses to locations. And so this function f, on receiving a packet p, is going to take the source Ethernet address from the packet and add that to the map so that it knows where, what port to send packets from that source from. And it's going to check if the TCP destination is 22, then return a null route. So this is a kind of security measure or access control that can be put in place. Otherwise, it's just going to retrieve from the map the location that it should send the packet based on the Ethernet destination. And then it can compute some path. Maybe it'll compute the shortest path in this instance, and then return that path. So it's doing a few different things here. It's updating its environment by updating that map data structure. It's reading packet data, and it's also computing and returning some path. All of these pieces are important because we need to be able to observe what the function does when it sees a packet in order to generate flow tables. So what the Maple programming abstraction can do is it's going to observe the dependency of f on packet data. And for every observation that it makes, or every series of observations, it's going to compute a trace. And a trace is basically a series of assertions or observations about what kind of read happens. And then the leaf of each trace is an action, so something like drop or it specifies a path. Once those traces are in place, they can be combined to build a trace tree, which is a partial decision tree for that function f. So at any given time, we may not have reached all execution branches of f, but whatever packets we've seen can be used to build this partial decision tree. The benefit of having the tree is that once we have that, we can easily generate flow tables from the trace tree. So this model is very flexible, and it'll enable some good programming abstractions. But it can introduce performance bottlenecks if it's naively implemented. And that's because the controller is probably not going to have the computational capacity to invoke f on every single packet. And on top of that, there's also bandwidth issues and latency issues. So in summary, Maple is an SDN programming system that enables this algorithmic model by addressing these performance challenges. It allows for simple and intuitive programming while achieving high performance and scalability at the same time. So that was the brief introduction of our project. Now we're going to talk about the tasks that we actually accomplished, the tools that we used to do it, the documentation that we used, and then finally at the end we'll do a demonstration of our project.